Okay, so we can listen now to Pierre Lescanne about the almost classical, all classical proposition of intuitionists.
Yes. So,
ça marche pas.
Ah, si.
Yeah.
Ah, si, oui, j'étais dans le modèle. Okay. In 2007, Marek Zayong, I hope he is here, and co-author address the following paradox. Asymptotically, almost all classical propositions are intuitionistic. So in this paper, I consider experimentally, so it's essentially the result of experiment I've done to know what almost means. Because, you know, it's very important to know whether this behavior of getting almost all the classical proposition arise with a small number or very, very far. And actually, the problem is that it's obviously the case that not all the proposition are classical, because there is this well-known Pierce formula, which is classical, but which is not intuitionistic. And also you will notice that I will focus essentially on proposition with arrow. It should be interesting to extend this to other operator like or and and, but it's still, for experiment, it's still difficult enough to focus only on arrow formula. So actually, the paper Jenny Trini and Kosix and Zayong was published in Type 207, and the title was Intuitionistic versus Classical Tautology Quantitative Comparison. So, and the three authors consider a data structure which I call in this paper, they didn't give it a name, and I will call it in this paper canonical expression. So I address those canonical expressions, namely they are implicative proposition, meaning that I use only the operator arrow or implication, and they are considered up to a renaming of variable, and which means that two implicative propositions are the same if they differ by renaming of variables. So better in actual implementation, I consider implicative proposition with a canonical naming of the variable, not to consider up to variable. So first, let me introduce the concept of restricted growth string. Given a list of variables of an expression of size 10, x, so x, y, y, x, y, x, z, x, 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 you can, because it's up to variable, you can write it another with other variable. And if we name canonically the variable, we get alpha 0, alpha. I name them canonically, but I will, for convenience, name them for right to left, and starting at the end. So alpha 0, and then when I get a new variable, I call it alpha 1, alpha 0. No, a new variable, I call it alpha 2, alpha 0, alpha 2, alpha 2, alpha 0, and which corresponds to the string of naturals, which is the string 0, 2, 2, 0, 2, 0, 1, 0, 0, 0. And if you look at the literature, they receive two different names. Knuth called them restricted growth strings, and Flageolet and Sedgwick call them irregular staircase. but more generally, they are a way to canonically represent an equivalence class. Now, I consider canonical expressions. So canonical expressions are binary expressions with variables which are named canonically by a restricted growth string, and which uses only the operator arrow. Hence, a canonical expression is a pair made of a binary tree and a restricted growth string. So for my experiment, let's say few things about those things. Binary trees are counted by Catalan numbers. That's something you may know. And I spoke about this yesterday. And restricted, and actually I was, anyway. A restricted growth string or equivalence classes are counted by Bell numbers, P sub n, and canonical expressions are counted by sequence, Kn, which is the product of Cn-1 times Pn. And it's known by this sequence on the OEIS. And there is, you can also give this approximation for Kn, which show that when we will generate formula, so from canonical expression of size n, you will get a very large number of them. And yes, also in this formula, R is the same as short for R or N, which is the positive root of the equation R e to the R equal to n plus 1. Okay? No. Okay, so in this work, I'm going to try to, what I will do, using a Monte Carlo approach, I will generate a random canonical expression and check whether it is classical and whether it is intuitionistic, and count the ratio of intuitionistic classical expression among classical canonical expressions. So I will generate them at random and try to get the ratio experimentally. So I use what this calls I'm not a Monte Carlo approach. I check properties on this object. I count objects fulfilling those properties, and I collect statistics for objects of that size. So this relies on an efficient and correct random generation algorithm, an efficient algorithm for checking properties at the price of checking only weak properties. Because if I trying to check whether a canonical expression is classical, it's extremely expensive, and also and even more checking whether a canonical expression is an intuitionistic one. So, but if you browse the literature, there are descriptions of efficient random generation for both components of a canonical expression for random binary trees, the so-called Remy's algorithm, and for the random generation of equivalence classes, there is an algorithm due to Stamps, so Stamps algorithm, which is also described in the Knuth, The Art of Computer Programming, Chapter 4. So those two, which has been cited this morning, so it seems to be a reference for us. So there is so the first result is a ratio of simple intuitionistic theorem. So a simple intuitionistic theorem is, I call theorem, so something that I can prove in intuitionistic logic, is a case when the goal is one of the premise. So a very easy case, effective. Actually, if one of the premise is your goal, the theorem is intuitionistic. And then I got, so you got this result this gives the ratio of the size of the expression and the.
What do you mean by goal?
The goal is when you have they are canonical expression where you have a p at the right of the last arrow. So this is the goal of your proposition. Okay. And among the premise, so among the propositions that are before the arrow, you get one which is also p. So this is a very simple case. So that's the result. Yes, this is only a result on the size of the expression, which is log n on n. I forgot what is Rn. Simple theorem are proposition with, so I call them simple theorem. The first approximation of intuitionistic theorem. Then symmetrically, you can consider simple antilogy, something I call simple antilogy, meaning that they are simple propositions that are trivially non-classical. And I found that the name antilogy is natural for those expression, which is symmetric with a simple theorem. So then this is simple theorem and simple ontology is the approximation of non-classical tautology, which I would, this is the way gender Trini, Kozik, and Zayong approximate intuitionistic versus classical ratio. And what they got so I limited the case for expression. I should have written this expression of size 100. I got 36%, and so at 100 you get already 36%. And you may show that this grow, but it means that when you get to 100, you are it's a rather limited ratio of propositions that are actually that are proven to be classical. And intuitionistic among then there is a big gap between, so at this point there is size 100, there is still a big gap between expression we know that they are classical, they are intuitionistic, and those we know that we know that they are so we know the size of those which are not classical. So you have in between. But more in my experiment, I generate 10,000. It takes time to generate those. It's the reason why I don't have a very big benchmark. But 10,000. Random classical expression, I found 338 simple theorem and 60 685 non-simple ontology, which this is from those numbers that I say that they are 36%. But to get further, I consider more elaborate notion of proposition. So there is another class of theorem, intuitionistic theorem, which are propositions of this form. They have a goal which I call alpha sub I, and two premises. One is alpha sub j, and another is alpha sub I implies alpha sub j.
Is there a typo?
Oh, so it's possible that there is a typo. Yes, there is a, yeah, here it should be like that. So it should be alpha sub j implies alpha sub I. Thank you. So these are the form in general. You see one of the premises is an implication alpha sub j implies alpha sub I, and then another premise is alpha sub j, and the result is alpha sub I, or they go in the other direction. And I call an easy theorem, so then you have a new class of theorem, the easy theorem, which is a theorem which is simple or NP. And then in intuitionistic logic, if a premise is a theorem, it can be removed. It is of no help to prove the final result. So what I can do is, in my experiment, I remove all the easy premises. So this way, I simplify the formula. And a minor theorem is a theorem of the form ... P. So you have it's not so notice that this is not a variable, it's a proposition. So you notice, so what you see is that in the tail of your sequence or list of proposition, you have a proposition which is P, and you check whether this sublist P doesn't appear as one of the premise. So this condition is rather expensive to check, because you have to check for a sublist. You look for all the sublist of the proposition, so of the tail, all the possible tail of the canonical expression, and you take it and you check whether it doesn't appear before. So it's since it's expensive, it will be detected only we are with an easy when the easy sub expressions have been removed before. So this way you expect to have smaller theorem. Then I define the notion of cheap theorems that are expressions that are either minor or easy after removing recursively easy premises. So you have a process which is recursive to simplify your proposition. This way, on canonical expression of size 100, I found that on the experiment, which has 96% classical tautologies are cheap theorem. So you actually, those that are candidates for to be classical tautology are, as you have seen, no. Actually, I was able on the expression of size 100 to actually check whether the proposition is classical. It is really among the classical tautology that I found so that are cheap theorem. This is because my classical method for checking classical tautology. It is not complete, but it works. It is able on those formula to tell, yes, those propositions are classical. It doesn't work on every case, but actually it works. That's maybe my chance, but it works actually on all the samples I've experimented. For instance, you know, I report here one of the results of my experiments. I generate a sample of 20,000 random canonical expression. I found, which takes about 1 week on the computer, on the computing station of the laboratory LEAP at Lyon. But I found 759 classical tautology, among them 733 are cheap theorems. So this shows this shows that actually we are much further than the previous result on the ratio of intuitionistic versus classical. But the status of the 26 remaining proposition in between is not certain. I don't know whether they are intuitionistic, but not classical, or they are classical. So there are 26 propositions with an undefined status.
These are propositions. These are just propositional logic.
Yes, from the beginning.
Yeah. I mean, so you could, presumably, there's decision procedures for intuitionistic propositional logic. So you could decide, you could determine.
But it's a complexity which is much higher. The problem is that it's untractable to check. What I wanted is to.
Okay, for these expressions are too big to determine, to decide.
Yeah, and you have to check that on 20,000 propositions of that.
But these 26. The 26,
yeah. Maybe what you say is that because there are only 26 remaining.
I don't know. I mean,
yes.
You could try.
Yeah, because I've eliminated all of them. But I don't know. I don't have an implementation of this, so which required to implement it. Is there a simple algorithm?
I think Dekov has he came up with a decision procedure using a sequence calculus, which I'm sure has been implemented. I don't know offhand of an implementation.
Yes, I can subtract. I can subcontract this to another implementation. That's possible. Yeah, to check, which means that we can even squeeze the constant. Actually, my idea also, what I've been behind, was to propose characterization that are simple enough so that a method like those that were used by Antoine and the other, the three, can be extended, because actually my definition to sieve the intuitionistic formulas is by recursive definition. So this, I imagine, I would be happy to work with people, can be applied to analytic combinatorics method. Do you agree? Do you think it's possible? But it's slightly more elaborated, but it should work.
Yes, it is probably technical, but it should work.
Yeah, and what would be interesting this way is to find a constant which is much smaller and which shows that the phenomenon of merging classical and intuitionistic arise much earlier. You know, according to your results, 30% for formula of size 100 is slightly deceiving. When if you get 96%, and we can even get more if we find other methods. You know, we find other class of formula like cheap formula. Okay, and so by implementation, I hope to do better. I mean, not, I don't, in my first step, I will use a language which is probably more efficient than Haskell, or maybe better method in Haskell. I'm taking advice on this. And I can go to formula further than 100, perhaps further we can get even smaller result, and by using analytic combinatorics should confirm first 96 of classical proposition are cheap theorems, and see whether because if we get an actual formula, we can go further than 100 and show that for larger formula, the ratio is even closer to 100%. So this is even more, and this is the end of my talk. Thank you for your attention.
Maybe you can speak loudly or something.
And the slide that you had with the random examples, you had these numbers that out of 20,000 random formulas, so many were classical topologies and so many were.
Yeah.
I mean, couldn't it be that the result that there are only so few, the 26 remaining, couldn't this depend on the choice of the random? I mean, how did you select those 20,000 random canonical expressions? The choice of that random function, how do you select them? I mean, it's a tree, right? That expression is a tree. So how you create that random thing could determine the results that you get at the end?
This is exactly what I say. I use these two algorithms. So Remy, I said at the beginning that a canonical expression is a pair of a binary tree and so an equivalence class. So yes, there is in CNUS, I found an algorithm for generating random binary trees and an algorithm for generating random equivalence class.
Yes, independently, but still, I mean, the choice of selecting the tree is
uniform.
It's uniform. It's uniform. Yes, it's a.
On the set of all the trees.
Yeah.
Okay.
Yes, it's a rather surprising result at first, but now we are used to. But at first, it was rather surprising that we look for classical formula, true classical formula, and actually there are rather few.
I know a lot of them. Maybe it's
few of them are simple. Because you just look at simple ones.
The intuitionist theorem, no, there are more that it's those that are called cheap. I try to give name for my class of formulas. I don't know if they are names already given in the literatures, but For me, what I consider as an intuitionistic classic canonical expression is an expression which is cheap, which is selected by recursively. So you eliminate all the theorem in the premise to get something smaller. Then you perform check, and then eventually when you have performed all the simple case and simple elimination, you perform what I call when I look for the tail, which is an expression, and whether it may appear at the beginning.
Yeah, I mean, it's similar to what happens in stats, right? So if you take a random formula and you want to have something, the very high probability, it's easy to solve it, right?
Yeah, yes.
And the ones that are hard are very, very few, right?
But that's a goal. You know, the goal of this workshop is to look probably on the hard case, trying to select what are the hard case. Actually, there are so few classical formula, true classical formula, and so how can we characterize them? Say the shape that they should have, that the kind of work combinatoriation likes to do, trying to characterize, and then we may answer why they are so interested that there is a large community of people among the type theorists who are interested by those formula which are classical and not intuitionistic.
Just to say, I mean, to follow to what Lutz said, it could be interesting to consider formulas which are hard in the sense that they're hard to prove or refute. Like in SAT, if you constrain, you can select the number of clauses and the number of variables, and then if those but there's a very narrow threshold where the SAT become hard, and so within that threshold could try to quantify of the theorems that are classical, how many are intuitionistic.
For me, it's clear. What I would state is that the hard classical formula, the hard for the SAT, are those among those 4% that are not cheap formula. Because they are method based on very basic method of intuitionistic logic, eliminate and sieve 96%, and there are a remaining of formula which are not evenly, not trivially checked to be true or to be a theorem. And then we should focus on those ones. And then among those ones, there is also a limit between those that are intuitionistic and those that are classical but not intuitionistic, which is also something which has to do with the threshold that Noam mentioned. I don't know, there are some things that appear here at that point.
Okay. Other questions online? No. Okay, yeah. So thank you again.
Maybe something in that direction. I mean, it's a bit, like you said, it's frustrating that most formulas are just trivial. And how hard would it be to consider, I don't know, something where you cannot prove the theorem using just a subset of the premises. You have to use all of the premises to prove the goal. I mean, such formulas would be rather interesting, but I don't know.
Those probably those are among the 4%. Those where the goal depends on all the premises, and not trivially.
In fact, it makes me think of a recent paper from Florent Queclin and Pablo Rotondo and Cyril Nico as well, where they prove that if you generate a uniform regex, regular expression, and if you simplify, for instance, if you have you have that A plus B star plus anything, if you have a two-letter alphabet, is just A plus B star, right? So if you have an absorbing pattern like this, something that simplifies the formula, in expectation, even if you generate huge formulas, you will have formulas of constant size, okay, or of constant size. It seems like something similar is happening. We can generate big formulas, but if we simplify and see that, I don't know, you have the goal in the premises, then the formula is not interesting. It would be better to generate something more less syntactic and more semantic. I don't know how to state this. To take into account the fact that there are simplifications.
I didn't count, but I imagine that when I remove all the cheap premises to get what I call minor proposition, a minor, then the minor proposition are rather small. It's what you want to say. Yeah. So, and then since they are small, the algorithm that check they are minor is cheap. Cheaper. It doesn't require much computation because, and actually, that could be possible to measure the size of the minor formula that I get eventually.
And when you remove these sub-theorems, you lose the uniformity. Because you have object of smaller size. You can say that you are
no, but
uniform at the beginning, but not after.
Yes, but the uniformity is obtained on the side of all the canonical expression. After all, I just wanted to confirm his conjecture that actually the minor theorem are small supposing that I've eliminated the cheap one on all the premises.
Okay, so I have to stop and move to the next talk. So thank you again. The talk online.